Thank you. So thank you, Bảo Châu, for the invitation to speak at the seminar. So my talk will be a continuation of Bảo Chau's talk. We'll discuss these Braverman-Kazhdan conjectures and for general reality groups. So basically, I will try to explain the idea of proof. So the key to deal with this conjecture in general is to somehow prove a more general statement. And moreover, you try to divide the question problem into two parts. The first part has nothing to do with this representation of dual groups. It's some pure statement about certain class or shift on reality groups I will call admissible. And you prove some classification or structural result of this class or shift. Basically, those admissible shifts are those shifts satisfy this vanishing property that Bảo Châu talked about in the previous lectures. And then you show that this class of shifts admit functorial transfer. So you have this nice property. If every time you have a map between your two groups and a map between their dual groups, then this class of shifts admit a transfer. And now to prove Braverman-Kazhdan conjecture, you just consider a case. You have a representation of dual groups. You started with the example, this kind of standard Fourier kernel on GON. And the claims that the transfer of this kernel is again admissible. And that's the claim of Braverman-Kazhdan conjecture. So now I will start with first fix some notations. So first, K will be the closure of Q. And we fix the L, it's not dividing by, so it's a characteristic P, not dividing P. And for any, say, stack over K, I would denote dx to be the bounded derived category on X coefficients, and mx to be the subcategory of perverse shifts. So these will be my notations. Okay. And so I will also fix characters, non-trivial character, SQ, identity characters. So non-trivial. And then from this, we have this Artin-Schweier shifts over A1. So this is the Artin-Schweier shifts on A1. Okay. So the Braverman-Kazhdan, this conjecture, in some sense, a generalization or nonlinear generalization of this well-known cohomology vanishing of Artin-Schweier shifts. So we know that so this vanishing has something to do with for analytic shift, where this powerful analytic Fourier transform introduced by the Lin. And this Fourier transform has some remarkable property, and I found many applications in representation theory, number theory, and algebraic geometry. And the key to establish those nice property of analytic Fourier transform is this cohomology vanishings. And so now I'll try to explain, actually, Braverman-Kazhdan's conjecture in some sense is somehow the nonlinear generalization of this cohomology vanishing. So I'll just consider the case, say GO2. So this part will be somehow will be overlapped with Bảo Chau's talk. So we can consider the trace map of GO2 to A1. Okay. And then you can just consider the pullback of Artin-Schweier shift. Let me denote it by the pullback Artin-Schweier shifts and maybe normalize like dimension 2, so that it's a perverse shift. So this is basically somehow the Fourier kernel for GO2. Convolution actions, but with this guy is like a Fourier transform for shifts on GO2. And now Braverman-Kazhdan somehow implicitly show that actually this kernel has some satisfy this cohomology vanishing property. So the idea is that, and this is somehow the shadow or somehow equivalent to the cohomology vanishing for Artin-Schreier. And it's just based on this linear algebra that Bảo Châu explained. So if you consider, say, B, which is the Borel, the upper triangular, so you have, so where B is just consists of this, and U is the unipotent. Then you consider for any, and let G be an element not in the Borel, so it consists of A, B, C, D, where C is non-zero. Then turns out if you look at the G, the coset, GU, and GO2, and you have trace map to A1, you just consider the restriction of this trace to this coset. And as long as G is not in B, this map is isomorphism. So this is a very simple computation. You basically compute A, B, C, D times 1, x, 0, 1. And you can check that the trace goes to, the trace is given by Cx plus A plus D. Okay? So as long as C is non-zero, which means that G is not in the Borel, then you see that this map is ABCD is fixed and X is varied. So the unipotent radical is just isomorphic to A1 in this case. So therefore, you restrict to this coset, it's isomorphism. And then from this, you see that the following. First, if you consider the cohomology of, say, of your sheaf, this kernel, Fourier kernel, restrict to this coset GU, and this will be nothing but just A1. So for GB, the restriction of your kernel to this coset is just because it is an isomorphism. So this map is an isomorphism. So therefore, if you restrict to this coset, then just the same as your Artin-Schreier sheet on A1. So this is 0 for all G not in B, and that's the vanishing statement in Braverman-Kazhdan conjecture. And you see that you simply just pull back Artin-Schreier along trace map. This sheet satisfies this property, and you can reformulate this in the following way. You consider the quotient map from GO2 to GO2 mod U, which is R. Then this property is the same as it consider straight push forward of your sheaf. And this guy is supporting on, it's contained in BU, which is subset. So you can identify this with T. So the support, so it's basically this sheaf is 0 outside the closed B orbits on this quotient space. Because if your point, you have some coset G, a point here is basically a coset of U, and if your point is away from the closed B orbits, then the preimage is exactly this coset GU. So therefore, by base change, this vanishing is the same as saying that when you push forward, you get shift on this usually basic affine space. somehow this thing is supported on the closed B orbit. So it's vanished outside the closed B orbit. And that's basically the proof of this conjecture in the case of 0 to n for this particular thing. And actually, you can generalize this to GON. You just pull back Artin-Schreier along trace map, and where you replace GO2 by GON. But then there's a similar type of a statement that Bảo Châu explained. And using that linear algebra for monobolic subgroup, you can also prove this kind of statement. Yeah, for standardism, for this particular, this guy, just pull back of Artin-Schreier along the trace map. Okay. And now, so Braverman-Kazhdan realized that actually, turns out any shift on the group with this vanishing property or equivalent with this support condition has some remarkable property. So therefore, it suggests that we should somehow first look at just shift on your group with this property and try to understand them. And now that will be my next topic. So for this, let me fix some notations. So let G be a connected related group over K. And again, we assume this is a split. So meaning that we have this Frobenius. We assume G is a split type. And we fix the U is a split Borel pair. And so I want to introduce a class of shifts such that this property, and I will call those class of shifts admissible shifts. So for this, I have to introduce some notation. So we can consider, so first, we have this so-called horocycle functor, which is, you can define the following functor, which is from shifts on G. Sorry, let me write. So let me denote G be the G quotient by G by the adjoining actions. Then you can consider the shifts, G equivalent shifts on conjugation equivalent derived category. And we also have, so let me write the following way. You can consider the following functor. So G, you first forget about, and then so this is an analog of this push forward, but because we consider G equivariant, so we don't have a map like this map in the case of a quotient stack, but you have a conjugation actions, then you can first just restrict to B, where this G mod B is Bx on G by the conjugations. And then here, so here is a forgetful map. And here is the averaging. So this is the integration averaging from with respect to U. So we integrate on one side, then because it's a conjugation equivalent on both sides with respect to B, you see that you get a shift which is U equivalent on both sides, and T acts on this by conjugation actions. So you get a functor from here to here. I denote this by R lower streak by abuse notation. So this is an analog of this functor in the equivalent derived category. And so now the analog of this class of shift is the following in the equivalent setting. So definitions. So first, I denote D, G, A. A stands for admissible. Just consists of those complexes in the G. With the property that when you do this functor, sometimes people call this a horocycle transform. Okay, this is supported on basically the closed B orbit. So it's a B, U, mod T. So it's a closed thing in G. So this condition is an analog of this condition in the equivalent setting. And also you can consider the subcategory consider just those which are perverse sheaves, which is the GA, and basically intersect with M G. So I will call those things admissible for complex or admissible perverse sheaves. So for example, in the case of GO2, this phi will be a admissible perverse sheaf. So we at least have one example in the case of GO2, such that this property. And in general, it's so first I will explain actually admissible complex and perverse sheaf have some remarkable property. So, and this is basically due to Braverman-Kazhdan. So they discovered that sheaf with those properties. Yes, Borel subgroup is enough. Yes. So we have the following fact. Due to Braverman-Kazhdan. So first, so if you have a thing which is admissible perverse sheaf, and you have any sheaf on the torus, Tx by T by conjugation action, so it's just a trivial action. So T mod T will be just T times Bt. Then we have this following property that I forgot I have to introduce parabolic induction. But anyway, let me first write down the convolution with inductions is isomorphic to inductions restrictions we come up with L. So to explain the notation here, so I will need to remind you the Lustig inductions and the restrictions functor. So we start with G. Sorry, we start with say G. Then it eliminate from B ma B, such a natural inclusion. And on the other hand, we have this quotient map to T. So let me go this P and this Q. Okay? And then from this, you can just pull back and push forward. You get functor from equivalency on G to equivalency on Tn, equivalency from T to equivalency on G. And that's the Lustig induction restriction functor. So we have these induction functors from shift T to shift G, and another functor back, which is restrictions. And the functor is given by K, just given by P and Q, and the restrictions, induction L, K is just you first pull back Q upper star and push forward P along. So that's the Lustig induction restriction functor. And one nice fact is actually these two functors are T-exact. So basic fact, so we have the following fact that induction and so it's due to, in the case of so-called character shifts due to Lustig, but in general case it's a result of Roman and Sasha Yongding. So Zukanik and Yongding, they proved that induction and restriction are TZ. So we map perverse sheaf to perverse sheaf. Okay. And now here, and the first property about this admissible perverse sheaf is that somehow it commutes with induction in the sense that, so here, this is a, so recall here, you have a phi. It's by definition, you have F1 and F2. It's by definition M, where M is a multiplication map. And same for the torus. And I use lower street push forward. So your convolution actions on the group. And basically it says that if it's admissible, then this convolution action, which is some kind of Fourier transform, it commutes with parabolic inductions. So this is one first property about admissible perverse sheaf. And this is a very formal statement. Actually, the proof is very formal. Okay. And now the second statement is that actually, if we endow with F with a wave structure, so that you can talk about trace for Beanies, and turns out the corresponding is admissible in a sense of Lamont's talk, namely that these actions on irreducible representation is constant on the Lin-Lustig packet. So if endow with for Beanies, isomorphism, then actually the trace for Beanies of admissible thing, so I denote a little phi, is an admissible functions. So I won't remind you let me just write one more thing. So here, admissible basically means that if you consider convolution with chi pi, it's given like chi gamma pi, chi pi. So chi pi is a irreducible character of a irreducible representation pi. Gamma pi is a constant. This is a constant because of Schur's lemma. And this, you can think of gamma as functions on the set of irreducible representation. This is called gamma function. And this gamma is constant on Lustig, on the Lin-Lustig packet. And this also explains the name admissible complex. Somehow the geometric categorification of this admissible function. So here gamma is the set of GQ such that, so then gamma, so pi, and this gamma is constant on the Lin-Lustig packet. So therefore, from these two observations, you see that this class of sheaf or perverse sheaf are interesting because somehow it gives a geometric codification of these admissible functions, like a stable function, if you like. And now the question is how to understand or how to construct object here. I give one construction in the case of GO2, which can be generalized to GON. You just pull back Artin-Schweier along trace map. And now I'm going to explain a description of this category in terms of just torus and the value actions. And then from this description, you see that this class of sheaf admits functorial transfer. And now I will just apply to the case of a representational dual group and apply transfer to this standard example for GON. And we get many objects here. And that's basically the statement of Braverman-Kazhdan conjecture. Okay? So now I want to describe this category. Or more precisely, I'll first describe the abelian admissible perverse shift. And for this, we need to use the following observations that, so this basically, these restriction functors, if you start with perverse shift G equivalent, a priori it maps to T mod T, but you can identify this with just perverse shift on T. It's important we work with abelian category. And we have this fact that, that actually this restriction means the lifting to W equivalent perverse shift on T. So namely, I denote this by risk W, G, and maps to T mod W. So W here is the vowel group. And so I think in the case, if a shift, so-called character shift is known, loosely known about this, but in general, I think it's, you can find the proof in Lamont and Latier's paper. And in the D-module setting, I think Ginsberg also have a proof of this. And this is essential in the description of this admissible perverse shift. Because it turns out, if you restrict to this restriction functor to the admissible thing, turns out will be fully faithful, and we can identify the image. And then we get a description of this admissible in terms of just torus and the vowel group. So now let me.
The rest is the same like with the rest W is the same like the rest W. The same functors or
No, it's a T mod W. It's a W equivalent perverse shift on T.
So you're not the functor that you're about to construct.
Yes, this is a fact that this restriction functor somehow admit lift to the W equivalent. In other words, if I take a G equivalent perverse shift, you take a restriction, parabolic restriction, it has a canonical W equivalent structure.
So it's a factorized.
Yes. It factors to W equivalent, then forgetful. Does it make sense? Okay. So now I want to describe a certain subcategory inside here, and then show that actually this restriction W will induce this equivalence category. And actually, this essential image of this functor.
For this functor, in fact, you just say that the shift you get on T is equivariant for the normalizer, and then after that you can divide by just by T.
Yeah, because for abelian category, there's no bigger, but for direct category, you need to be careful. So, for example, if you look at Lamont's paper, it's quite subtle there. If you work with the direct category, I think in general there's no such functor to you have a T mod N. But for abelian, this is okay. Okay, so T structure plays a role here. So now I want to explain the image. And turns out this the description somehow comes from it's inspired by the proof of Chen and Go on Braverman-Kazhdan conjecture for GON. So I will introduce the following category I will call admissible shifts on torus. So now let me. So for this, like CT be the set of 10 character of your torus. So basically consists of pi, which is pi 1, 10 to be the set of 10 characters of T. And then we can, then turns out there's a many transform. So from perverse shifts on T mod W, first perverse sheaf to coherent sheaf on this thing. So this is the Mailing transform introduced by Garber and Losov. Garber. And then this boundary somehow descend to, you can talk about W equivariant. So it's easy to see that the functor is equivalent with the value actions. So value acts on T, and also value acts on the characters because it acts on the torus. And then you can introduce the following category I denote by MTWA, which consists of those equivalent perverse sheaves with the property that if you consider it's a Mailing transform L, but somehow you have to twist the forbidden structure by the sign characters. So this a priori is an object here, and you want this descend to the actual GIT quotient. Sorry, there's no A should be outside. So we consider those W perverse sheaf with the property that you consider it's Mailing transform, you get a coherent sheaf on this modular space or 10 character. And a priori it's a stack quotient, but you want this sheaf actually descend to the GIT adjoint quotient. But somehow you need to twist the equivalent structure by sign. I will give an example. You see that this is absolutely crucial. Okay? And this admits a more elementary decision because this involves this non-trivial Mailing transform. And more concrete decision is the following. You just consider of L, is reduced for perverse sheaves. Sorry, perverse sheaves on the torus. You have this property that you consider it's a cohomology, and you tensor with L chi. So here for each chi, for chi in CT, we have this corresponding L chi, which is a character sheaf, rank 1 local system on the torus. And I denote W chi is the stabilizer W in such that L chi isomorphic to L chi, stabilizer of this character sheaf. And if you consider this cohomology, it carries the action of the stabilizer. And you want this cohomology just the direct sum or sign representation. It acts by sign for all chi in CT. This is a more elementary distinction. So basically, you have a W equivalent perverse sheaf. For each character, you can consider the cohomology group. It carries a natural action of stabilizer of chi. Because L is a W equivalent, L chi is a W chi equivalent. So therefore, this guy is W chi equivalent. It acts on the cohomology. And you want this action just given by sign character. Okay?
Why should it be equivalent to
Why this is equivalent to this? This comes from the descent criterion that if this is true, then it's fully you consider it's a Mailing transform, then it's a derived stock carries the action of stabilizer. And the action is all trivial. Turns out it's equivalent to descent condition. You have no derived stabilizer in some sense. It's a descent criterion for coherent sheaf on the Tsao-Hsien scheme. Okay? And for example, this is somehow inspired by Chen and Go's work. For example, you can consider basically from Deline's work on this sign action and Kloosterman sheaf, you consider torus to A1 given by trace, you pull back along Artin-Schweier along trace map of torus, then this object turns out is in this admissible thing. And one, for example, you just consider L chi to be trivial, it means that the action is given by sign character of W. And that's Deligne's result. And this is somehow a kind of generalization for arbitrary W equivalent shift on torus. I will give more example later. So I'll first state the statement, and then I will give examples. Okay? Okay, so now here's the theorem. Sorry?
Restriction to 10.
The
No, because you consider only 10 characters.
yes. We only consider 10 characters. Yes. Because the many transform is transformed to moduli space shift on 10 characters.
That's enough.
Yeah, that's enough. Yes. The reason is, I can explain maybe, the reason is that, for example, this many transform is conservative. So,
The statement of Gaber-Lazar, I don't remember exactly what it proved.
yes. So the fact that the many transform is conservative has something to do with that we only need to consider 10 twist. Yes.
And they don't have an inverse in this case.
Yes.
They just prove some injectivity or something.
Yes. Because in the end, it turns out the general pool of reduction to temp scene, and you want to prove something is trivial for non-temp scene, turns out you only need to prove things for temp. And this somehow essentially reduced to this fact that many transform, to test the many transform is, or in other words, you have this fact that actually this L, if this L chi is 0 for all chi, then this actually is 0 for any non-necessary temp thing.
Not necessarily 10.
Yeah. I think they contribute this to you in the paper. They say that it, yes, so that's somehow, yeah, it's for any L, not necessary temp. So that's why somehow temp is enough. Okay, so now the statement, so theorem. I put a question mark because half of the theorem is still work in progress. But the statement is just saying that this, if you restrict to W is equivalence to admissible thing. And it's an equivalence and with inverse given by just a restriction W. So basically the content is that if you start with admissible shift on the torus, then this the induction, oh, I forgot to, so here, this is the induction W is a joint of restriction, and it's given by L. It's given by induction L. You take W invariant factor. So this is the adjoint of a restriction W. And the content is that if you start with admissible shift, then you take induction W, this shift will satisfy this cohomology vanishing property, just like the Artin-Schweier vanishing. And this part is actually written down. And the other part is if you start with admissible perverse shift, you take a restriction W, turns out it's a W equivalent shift, but actually it's still inside this category. Has this kind of stronger property. No, there's no cuspidal object here. Yeah, because the restriction is non-zero. Yes. Yes. All the admissible shift will be a summand of induction.
So this theorem explains why in what explained Hugo, you have this, when you go from the case of GNN to a torus, you have to change the action of W with this different sign.
Yes, I will come. Yeah. Yes. I will explain this when I talk about transfer. So that will be the next step. But here, just a decision on this category in terms of T and the W. And at this point, and the content is that the induction of your object here said that is cohomology vanishing. Okay. But at this point, it's still not clear how to construct object here and here. Okay. You have this thing, but still how to construct object in here or equivalent here. I only give you one construction. For GLN, you pull back Artin-Schreier along trace. Turns out next I will explain transfer, and then from transfer, for each row you get an object. And that's basically the content of a Braverman-Kazhdan conjecture. Okay, so but let me give you an example here. So for example, you can consider this delta shift on torus, just supported at the point, but you have to twist by the sign. And this is it's a admissible shift on torus. And if you take induction W, delta sign, it's known that it's again delta. So this is the induction delta W. But you have to take sign. And it's well known that for Springer theory, you need to take sign in order to get a delta shift on the group. It's clear that delta shift is a admissible shift here and also here. And it's also clear that delta shift satisfies this cohomology vanishing property. Okay? And also another example is actually the GLN examples. You can take this phi GLN, which is the trace map of Artin-Schreier, but you shift like n squared. And torus Tn. You have a trace from the torus, Tn to A1. You take pullback, and it turns out this is an admissible shift on torus. It's basically the Lin's sign action result on Kloosterman shift. And the corresponding admissible shift on the group is the one we GLN, which is just the pullback. Again, the pullback of a trace map, but now for the whole group. Again, Artin-Schreier, where you shift by n squared this is not dimension Tn by the thing, so that you get a perverse shift. So that's kind of two examples, very different one. And now I want to explain how to construct more examples. Okay. Well, actually, I think I can give you one more example. It follows from Lustig's theory of character shift. So you can take pi L dt, chi in Ct, which is generic, namely W chi is trivial. Then you can consider LW chi sum over W. And this is actually in A for generic character. And you can see that the induction, let me call this L chi bracket, is W L chi. It's just nothing but the induction of your, say, chi. For generic character, you take induction, then that's enough. It's then as you first W averaging, you take induction, you take W invariant factor. Turns out they are the same. And it's clear that if chi is generic, easy exercise show that if you do this whole cycle transform, you can only support it on the closed orbit by general stabilizer argument. But turns out there are many examples like this where you start with 10 characters. It turns out it's non-trivial to construct things where you start with a local system which is not 10, like a Kloosterman sheaf. But on the other hand, functoriality for finite fields suggests that there should be many objects like this associated to each representation of the dual group. So now let me explain the transfer. Oops. So say you have a map G check from G check to check. So now we have so far the discussion before has nothing to do with the representation of dual group, but now we're giving this data a map between dual groups. Then you have a T check. It first maps to L1 check, which is a centralizer of G check of the image. And we pick a torus here. Okay. And I load this T check, the resolution to T check. And now you can dual back. You get a map from T1 to T. Okay. And here you have value actions. And here, first from here you get a map row W, which is from the vowel group, which you can think of as N, G check, T check to T check to the vowel group of the Levy. So not the Levy, but this N G1 check of the Levy, which you can prove that is isomorphic to the normalizer of W1, WL1 mod WL1. So if you have a natural map like this, so therefore a priori you only get a map to this normalizer. Sorry? W1 is the vowel group of a G1. Okay. But then you can just pick a lift. And this normalizer of a L1 acts on T1. Now the claim is that, so here's the claim. So let me write down the claim. So basically here you have this diagram for any, I probably need this. So let in the T1 W1 admissible, and let L be just the push forward row T. Row T is this map to of L1. Okay, so we have L1 here. You start with shift here, then you push forward here. The claim is that this guy turns out admit a canonical W equivalent structure. Then, so the first statement is for any W in vowel group and any lift W1 prime in normalize F1 of row W. We have, I have to erase.
L1 is N or?
N1 is the normalizer.
Yeah, but L1 is in.
Oh, yeah, sorry.
No, but
W, L.
it's a Braverman-Kazhdan or complex.
Here is an arbitrary complex.
Do you define admissible for T?
Oh, yeah, I haven't defined this, but the same definition. So basically, you talk about, for example, this definition makes sense for any object. So for any L, yeah, I forgot to mention that this definition makes sense for Dirac category. Sorry. Okay. And so we have this diagram, T1 to T, T1, T here, W, W1 tilde, rho W, sorry, rho T. And you see that we have a natural isomorphism from pull back to W. And then actually, you consider the twist W1 tilde, which is, sorry, a W1, but you have a sine W and a sine W1 tilde. You twist this one, depends on the choice, but by these two characters, turns out depends only on W, and the collection BW, which is BW1 tilde, defines a W equivalent structure. W equivalent structure on L. So W equivalent structure on Dirac category is easy because W is a finite group. And now the second claim is actually this W equivalent is nice in the sense that actually this L, the TW, is actually inside this category admissible. Okay? So this is basically a generalized construction of Ngol's talk where G1 is a GON. If you replace G1 by GON, a representation, then that's the construction of a W equivalent structure on closed machine. And this property is basically Delign's sign action statement. Okay? Now with this construction in mind, I can state a transfer result, which will be the end result. So let me. So the transfer, you have this functor from N. So you have a row check from G check to G1 check, arbitrary row. Then turns out you have a functor denoted by T row, which to, because we consider arbitrary, the transfer will make perversity to, in general, not perversity, but that's okay. Sorry, should be G1 to G, admissible. And the functor is given by, you first have this equivalence to T, A, and then you just push forward. You have A, so here's one here, and then you have this induction W. The claim that you have this functor, this is a restriction W1, which is equivalence. You have transfer on torus as I explained there, and then you get induction back, you get the admissible thing. Here, the content is actually the induction map admissible to admissible extend to Dirac category. It's not clear for the restriction because involved with W equivalent structure in the Dirac category, but the induction step is actually extend to the Dirac category. And so you have this transfer from admissible thing on G1 to admissible on G2, as long as you have a map between dual groups. And now, finally, the example, you just consider row check, G1 to GON. You take, and then you take phi G of n, which is a trace. G of n, the one we have before, beside. And this is in admissible G of n, G of n. And the transfer will be actually the inductions W of this Kloosterman shifts T rho that Bảo Châu talked about in his talk. And this is in admissible G, in the admissible category for G. So you start with something on G. So here, so G1 is a G of n. You start with something on G of n, which is just the Fourier kernel. And then you apply transfer, you will get another object admissible here. And that's basically the Braverman-Kazhdan conjecture. Okay, and I still have 5 minutes. Let me briefly explain the proof. For example, how to prove this kind of, essentially you need to prove that you start with admissible thing, you take induction and satisfy this vanishing property. Actually, in the case of G of n, you can use the technique developed in Chen and Go's paper to prove this. It turns out you look at the proof, the only thing you use is these are definitions, these kind of sign character on Kloosterman shift. You abstract this condition out, you run the whole argument, you get another paper. So basically, that's how you prove this for G of n. But in general, you don't have Meraboli groups. So the idea is, turns out, this vanishing statement is somehow geometric, so makes sense in any shift theoretic setting. Actually, you can first prove this for D modules. Using a fact for D module, you can really write down explicitly those character D modules. And you can prove this just by computations. And then you also have this reduction to 10 case, as we discussed before. And then, as Lamont suggests, actually, if you reduction to 10 case, you can use some spreading out argument to deduce the positive characteristic case. And that's somehow the proof in the analytic setting. But the drawback is that for this, this proof only works when P is large, because you have this spreading out technique.
What is the statement of the theorem? Because you define T rho in this way, or you...
Yes. Yeah. So basically, the statement is that your restriction and rho and induction, it will map A. A priori, it's not clearly map A to A. Yeah. You not go to A, you go to those things which is admissible. So therefore, this function you get is actually admissible function.
The statement is that you get it.
Yes. Oh, yeah. I forgot to say that the remark is that so Lamont and Latier prove all of this in the setting of functions. Setting of functions. So for functions, Lamont and Latier, they prove also this general transfer thing. You start with admissible function, they write down the formula. And you can check that it's compatible. It's compatible with this geometric formula. And so it's somehow the shift theoretic or geometric version of their result. Okay, so I think I'll stop here.